Okay, so we just want to clean up a few details from the last video and introduce the idea of initial value solutions. All right, so in the last video, we had seen the following, that when we looked at dy dx equals 2y, we saw that that is a differential equation, and it had two true solutions that we looked at. Y equals e to the 2x and y equals 3 times e to the 2x. They were both solutions. Well, you might have figured out, okay, there might be other solutions as well. In fact, in anything in the form of y equals, let's make this an a for a constant, times e to the 2x will in fact be a solution. All right, it will work because if you take dy dx, the constant a is going to stick around, so you will have twice a e to the 2x being the derivative. And if you substitute that in over here, we have twice a e to the 2x should equal 2 times y, which is a e to the 2x. So no matter what the value of a is, it will still, a times e to the 2x will still be a solution. So all values of a work. Okay, now what does that mean? That means y equals a e to the 2x is called the general solution. You can put any number that you want in for a, and it will still make the differential equation dy dx equals 2y true. All right? Now, this is where we get to initial value solutions. What if we want the solution which passes through the following point through 0, 3. Okay, now this is why we call them initial value solutions, because you can see we're looking when the input is 0, all right? But it's a little bit of a misnomer because we'll do an example in just a moment where the input doesn't start at 0. But you're given a starting value. We don't have to start at 0, but for these problems, you're given a value through which we want the solution to pass. So you could think of that as a starting point or an initial value, even if it's not at 0. All right. So how do we find that? Well, we simply take the general solution and we substitute in the point, and we would see that 3 goes in for y, must be a times e to the 2x. 2 times an x is 0, 2 times 0. And e to the 0 is 1, so 3 is equal to a. So the solution that we had given before, y equals 3 times e to the 2x, is the initial value solution. That goes through, I'll say, just put dot, 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 that goes through the initial value 0, 3. All right. So notice now this is a general, this is a very specified answer. All right. You could put that in your graphing calculator and graph it. Whereas if we look at the general solution, there are an infinite number of graphs that we could form that are in the family of a times e to the 2x. So the general solution, would have things like 2 e to the 2x. You could even have 3/7 e to the 2x, or even pi times e to the 2x. Those would all work. So you need to know which one to use in order to make a graph of the solution. So this is the solution that if we were to graph it, would in fact pass right through the point 0, 3. Let's find the solution which passes through, let's say, 2, e to the 4th. Right? So notice this is an initial value solution, but our starting point is not at x equals 0, it's at x equals 2. We just do what we did before. We substitute in e to the 4th for, whoops, I meant to change colors there. E to the 4th is going in for y. so we're taking the general solution. We put e to the fourth in for y. That has to equal a times e to the 2 times 2, okay, because x is 2. And when you look at that, that is e to the fourth. So e to the fourth needs to equal a times e to the fourth. Therefore, a must be 1. All right, so that would be the other solution that we had looked at in the previous video that was true. That would be y equals 1 times e to the 2x. So that is the initial value solution that would pass through the point 2 e to the fourth if we were to graph it. All right, so there are an infinite number of initial value solutions depending on where you choose to as your starting point. All right, so the general solution leads to an infinite number of possible specific or initial value solutions. Let's just consider the initial value solution for our other differential equation that we've been working with, the cooling coffee equation, dt with respect to time, I should say derivative of temperature with respect to time, negative 0.05 T minus 20. And we saw that there was a solution to that where we saw that T was equal to 80 e to the negative 0.05 T plus 20 was a solution, but also T was equal to 60. We didn't actually show this one, but I said you could work through it just like we did the other. That would also be a solution, right? So you can see that the only thing that changed between these two solutions was the coefficient in front of the exponential part. And so you might believe that the general solution to this is a e to the negative 0.05 t plus 20. So this was the general solution. Okay. Well, if we want an initial value solution, let's find out the solution that starts at 100 degrees Celsius at time 0. So let's substitute in 100 for the temperature is equal to a e to the negative 0.05 times t. Oh, that's just e to the 0. We can just write in a 0 there, plus 20. E to the 0 is 1. So a must be 80. So that corresponds to the specific solution that we had used in the video. All right. So that solution would be the solution for when the water starts at 100 degrees Celsius. In other words, it was boiling and then we let it cool down. The other solution turns out to be, we must have started at a lower temperature. But we could actually have an initial value solution that is actually more generic. All right, so our general solution looks like this, but we could rewrite, if we're clever, we can rewrite A. Okay, so no matter what the case is, we could say that T is equal to, let's call this T initial, when that's the temperature, is equal to an initial temperature when the time is 0, right? So generally, instead of putting 100 in over here, we could put the initial temperature over here must equal A times e to the 0 plus 20, right? Well, e to the 0 is 1, so we could say A is always the initial temperature minus 20, which remember was room temperature, all right? So A would be the difference between the initial temperature and room temperature. And so we could more generally write that for cooling, in this case, T is equal to T naught minus 20, e to the negative 0.05 T plus 20. So therefore, the other example that we had where we we put a 60 in as the A value, means that the initial temperature must have been 80 degrees Celsius. Now, we could have different cooling. Right now, we're working with a specific cup, which has a cooling rate. Let's go back to the equation, which has this cooling rate. If you had a different cup with more insulation, if it had extra insulation, the cooling rate might be slower. Maybe we would lose 1% of the temperature difference every minute, okay? Or if you had a super cryogenic kind of mug, maybe it'd be something like 0.001, all right? And you could keep things cool, or I'm sorry, keep things warm for a long time if you could bring that number down by using lots of insulation. So the solutions we're looking at are all assuming that we're having a 5% temperature loss at any given time. But we could generalize this to, maybe a negative R instead of giving a specific value. And then if we go down to our final solution, this could simply be RT instead of 0.05T. So we could have any cooling rate that we wanted, and we could generalize how things cool using that formula, all right? But an initial value solution is something you could literally graph in your calculator and plug in, changing, using Y as your output and X as your input, whereas the general solution is a whole set of solutions that would be possible.